We're going to work a problem dealing with rigid body velocity that deals with gear ratios. So we've got two gears, gear A and gear B, and we know that gear A is fixed and it's rotating clockwise. We have an angular speed of omega A. And then gear B, with the no-slip condition, is going to be rotating counterclockwise with an unknown speed, omega B. We know the radius of each gear. We're given RA and we're given R sub B, which are scalars. And then we need to find two things. So first we'll calculate the degrees of freedom in this system with two rigid bodies, and then we'll find the speed, omega B, in which gear B rotates. For a rigid body that's operating in three-dimensional space, then it actually has 6 degrees of freedom. And that would be 3 translational degrees of freedom and 3 rotational degrees of freedom. Now in this class, we're only working in two-dimensional space, so instead of 6 degrees of freedom, we only have 3 degrees of freedom. And so with 3 degrees of freedom per rigid body, which are 2 translational degrees of freedom, and then 1 rotational degrees of freedom, in this problem we have 2 rigid bodies. Now we developed an equation in particle mechanics in which we said our degrees of freedom of the system will be m, so for m degrees of freedom is equal to the number of degrees of freedom per rigid body, or per body. So in this case we have 3 degrees of freedom per rigid body, multiply that times n rigid bodies, and then we subtract k, and that's where k is the number of constraints in the system. And so with n equals 2, we have m is equal to 3 times 2 minus the number of our constraint equations, and so we get 6 minus k. So we're starting off with 6 degrees of freedom, and we need to figure out what all of our constraints are. One of the first things that we read in the problem is that these are 2 fixed gears. So it means that the origin of gear B and the origin of gear A are fixed. They're not moving, so we know the velocities of those points. So we'll give these O prime and then O double prime for the origins of those gears. And then we come up with 2 vector constraint equations, which are 4 scalar equations. And those equations are the velocity of O prime as observed in the inertial reference frame, this is a vector equation, is equal to 0. And the velocity of O double prime, as observed in the inertial reference frame, is also equal to 0. And so from these constraints alone, this gives us 4 constraint equations. The next thing we know from the problem is that these gears have interlocking teeth, so there's no slip between them. So this is going to cause another constraint, and this constraint comes at the interface between gear B and gear A. And so let's call this point C. And what happens is at this point C, the velocity of the point on gear B and the velocity on the point gear B on gear A is the same. And so we write this by saying that the velocity of the contact point C, as observed in the inertial reference frame, on gear A is equal to the velocity of that contact point, as observed in the inertial reference frame, on B. This gives us one more constraint equation, and so then k is equal to 5, and so m will be 6 minus 5, and we get a 1 degree of freedom system. And this 1 degree of freedom system should make sense because our input into the system is omega A. That's our speed of the system, and as this turns clockwise, then gear B is going to turn counterclockwise by necessity due to these conditions. Now let's use our knowledge about angular velocity to solve for the speed at which gear B is turning in this problem. First, we need to apply our reference frames to the problem. So attach an inertial reference frame to the space, And here we define our origin as the point O and three basis vectors e sub 1, e sub 2, and e sub 3. We've defined these vectors as e sub 1, which is pointed to the right, e sub 3 pointed out of the page, and then e sub 2 is the cross product of e3 and e sub 1. We need to affix reference frames onto the rigid body A gear and also the B gear. And so for reference frame A, let's add a point Q to the edge of the gear. Attach a reference frame, and the reference frame is going to have an origin of O double prime, and then A1 pointed this direction, A2 pointed that direction, and A3 out of the page. And so in definitions, it looks like this, where we have A2 is defined along the line O double prime Q, A3 is coming out of the page, so it's the same as E3, and then A1 is equal to A2 crossed with A3. We'll add a third reference frame after we define the point P, which is on the edge of gear B. And so reference frame B has three basis vectors, B1, B2, and then B3. The origin is O prime. B1 is defined as along the line O prime P. B3 is the same as E3 and is the same as A3, and then B2 is the cross product of B3 and B1. I want to remind you to take your time defining these basis vectors on these reference frames, because this is a critical step, particularly in rigid body mechanics, that if you mess this up, then it's going to throw off the entire problem, and the mistakes are simply going to propagate all the way until the end, and you won't get the right answer on anything. Now, to work this problem, we want to apply essentially our constraint equations. And we're going to start with the constraint equation in which we have the contact point on gear A. The velocity of the contact point on gear A is the same as the velocity of the contact point on gear B. Now, we've defined 2 points, point P, which is on gear B, and point Q, which is on gear A. And when these rotate, we can put Q along with A, and wherever they contact, that can become our contact point C. So to solve for this contact equation, or for this constraint equation, we're going to set the velocity of P with respect to O as observed in the inertial reference frame equal to the velocity of Q with respect to O as observed in the inertial frame. And this is only true when P and Q are that contact point C. So let's solve for each of these velocities and set them equal to each other. Let's solve for the velocity of Q with respect to O as observed in the inertial reference frame first. So first we need our translational component, which is the velocity of O double prime with respect to O as observed in the inertial reference frame, plus the velocity of Q with respect to O double prime. We apply one of our constraint equations, which is that O double prime isn't moving as observed in the inertial reference frame, so it's equal to 0. So that means we only have the rotational component left, which is omega A as observed in I crossed with the position vector RQ with respect to O double prime. Now we know that the wheel A is moving clockwise according to our problem statement. So we can write this term as omega A in the negative A3 direction crossed with the radius R sub A in the A2 direction. Because we defined our position vector from O double prime to Q in the positive A2 direction. Working out this cross product, we get the radius R sub A multiplied times omega A, scalar, in the A1 direction. Similarly, let's find the velocity of point P with respect to O as observed in the inertial reference frame. And to do that, our translational component is the velocity of O prime with respect to O in the inertial reference frame plus the velocity of P with respect to O prime in the as observed in the inertial reference frame. We have a similar situation in which the velocity of O prime with respect to O observed in the inertial reference frame is equal to 0. And so then that reduces our problem to the velocity of P with respect to O as observed in the inertial reference frame is equal to omega B as observed in I crossed with the position vector of P with respect to O prime. We're solving for the angular velocity, omega B, so we don't know its direction. We'll just assume it's a positive scalar, so we'll put it in the B3 direction, and then we're going to cross this with the radius of the gear B in the B1 direction, because that's how we define the position vector from O prime to P. And so we obtain the velocity of P with respect to O as observed in the inertial reference frame is equal to the radius r sub B multiplied times the angular speed, omega B, in the B2 direction. And so when we set these equal to each other, we get r a omega a in the A1 direction is equivalent to r sub B omega sub B in the B2 direction. Now we still don't have an expression yet for omega sub B because we have a mixed basis. So our left-hand side is in the A1, or is in the basis for the A frame, and our right-hand side is in the basis for the B frame. So what we need to do is take a look and see how these vectors relate to each other. How does A1 correspond or relate to B2? And when point P and point Q are the same point or in contact with each other, when they align, then what we have is the vector B1 is pointing toward P from O prime to P, and then the vector A2 is pointing from O double prime to Q. And so we see from this that B1 is equal to negative A2. And in addition to that, we have our B2 vector, and then we have our A1 vector. These are pointed in the same direction, so B2 is in the same direction as A1. We make our substitutions, A1 in for every B2, and so we get the expression RA omega A A1 is equal to R sub B omega B A sub 1. And then the relationship between these parameters is we have omega B is equal to R sub A over R sub B multiplied times omega A. So what we see here is that the angular speed of gear B is equal to the ratio of the radius of gear A divided by the radius of gear B multiplied times the angular speed of A. Now, this is a positive relationship because we've already taken into consideration that omega A is turning in the clockwise direction. We did that by calling it negative in the E sub 3 direction, or rather negative A sub 3 direction earlier. This ratio of the radii is called the gear ratio, and in this situation the radius of gear A is less than the radius of gear B. So therefore the angular speed, the magnitude of the angular speed of gear B, will be less than the magnitude of the angular speed of gear A. So the big wheel rotates slower than the small wheel. And you use this in your mechanical design to change an angular speed to a higher angular speed or a lower angular speed, and this is how you keep track of that with the velocities.